In order to see this one-to-one correspondence, first we show that phi is one-to-one. I mean, in order to see this bijection, first we show this phi is one-to-one, and we prove it by contradiction. Proof of the claim. That means we suppose there exist two distinct elements that have the same image under phi. So that means P1 minus O is equivalent to P2 minus O. And by the arithmetic of the divisors, this means that P1 and P2 equivalent to each other, and by the definition of the equivalence, again, we consider a function whose principal ideal is the difference of P1 and P2. And if you consider its zero divisor and the pole divisor, indeed, we can see that these places gives us the zero divisor and the pole divisor. But on the other hand, if you consider the expansion degree of the R elliptic function field over K of X, we know that it has extension degree too, but in this case, we get the extension degree 1, so that means the genus 0, and this gives us contradiction with the definition of elliptic function field. So that means phi is one-to-one. Next, we want to see that phi is onto. So if we take a class group or the equivalence class from the Jacobian, so that means it is degree 0, but this is not supposed to be a principal divisor. We can consider the divisor A plus O, which is obviously degree 1, and this is bigger than or equal to 2G minus 1. Ben Bayli Riemann Roth theorem. We can compute its dimension as 1, because this is going to be 1 and the genus is 1. And since this is a non-trivial vector space, again by the same trick, we know the existence of a positive divisor, effective divisor, which is equivalent to A plus O. Consequently, they have the same degree with consequently with the same degree A plus O. And again, as we have considered in discussion sessions, for a positive divisor with degree 1, we know that it can be only rational place. And indeed, this rational place gives us the pre-image of this equivalence class. So that means PO is equivalent to A. Now, thanks to this correspondence, we can endow the rational set of rational places with addition. That means we can define a group structure. The operation is denoted by A plus, inside of a circle on the set of rational places, and we define this addition depending on the additive structure of the Jacobian. And recall that our map is defined as the equivalence class of P minus O. O denotes the base point or the place at infinity for the elliptic curve. And if you consider this operation, please check that this gives an abelian group on PF1 with specified identity O. Here, let me point out that this group law, indeed, I mean, its definition is depend on the choice of the base rational place O. I mean, we can there can be another places, rational places, or the place at infinity for the elliptic function field. But after fixing this base point, we define the addition. But the group theoretical structure of the set of rational places is independent of this choice. So whatever, always we can choose degree 1 place, which can fix it as a base point, and always we can identify this bijection and this group structure. But in particular, it depends on the choice of the base field. And finally, as a last example, we briefly consider the hyperelliptic function field. So again, we will define these function fields in terms of their genus. In this case, instead of using a description by the degree, actually we will see that it's also possible to describe it if it contains degree 2 places, but in general it is defined as the quadratic extension of the rational function field K of x. Indeed, as an alternative characterization, we can also observe that a function field with genus bigger than or equal to 2, then we see that F is hyperelliptic if and only if it contains degree 2 divisors and of dimension at least 2. Moreover, we will also see that every function field of genus 2 is hyperelliptic. So for instance, in the rational function field case, we see that to characterize the rational function field in terms of genus is not enough. We also need the degree 1 divisor. But with respect to this definition and this characterization in part 1, we will see that every function field of genus 2 gives us hyperelliptic function field. In order to prove the first statement, let me suppose that F is hyperelliptic first, and by the assumption we know that genus is at least 2. Then by the definition of the hyperelliptic function field, we can choose a function which gives us, which allows us to view I hyperelliptic function field as a quadratic extension. And particularly, let me also consider the pole divisor of this transcendental and denoted by A. So since this extension degree is 2, we know that indeed it is also degree of the pole divisor. So in this case, degree A is 2. Moreover, we can also observe that 1 and x are functions in the Riemann-Roch space, and they are linearly independent over K. And this also shows us the dimension of the divisor is at least 2. And indeed, this choice, the choice of the transcendental gives us the desired divisor with degree 2 and dimension at least 2. Now, let me suppose that conversely, there exists a degree 2 divisor with dimension at least 2 in the function field of genus at least 2. Since dimension is bigger than or equal to 2, we know that it's not constant field and it's not non-trivial vector space. Again, the same trick. We can see the existence of an effective divisor which is equivalent to A. And by this equivalence, they have the same degree and they have the same dimension. And with respect to this effective divisor, we can consider a function inside of its Riemann-Roch space, which is not constant. So that means its principal divisor is bigger than or equal to minus A prime. Here A prime is positive. So that means we can only compare the pole divisor, the coefficients of the pole divisor, and the coefficients of this effective divisor A prime. Indeed, it means that minus x infinity is bigger than or equal to minus A. So the x infinity is less than or equal to A prime. And so that means the degree of the pole divisor, or the expansion degree of the pole divisor, is at most the degree of A prime, which has the same degree with A. So this is 2, and this extension degree can be at most 2. However, on the other hand, we also know that this genus is at least 2. That means this extension degree cannot be 1, because if it is 1, we get our elliptic function field as a rational function field, and this gives us contradiction because we get the genus as 0. So that means this we get this inequality only when the extension degree is 2. So that means if there exists a degree 2 divisor with dimension at least 2, this gives us the quadratic extension. That means elliptic function field. And finally, to see that indeed every genus 2 function field is hyperelliptic, indeed we can use the equivalence in the first statement if we are able to see the existence of degree 2 divisors and the corresponding Riemann of space has dimension at least 2. By using this characterization, we can conclude that F is hyperelliptic. On the other hand, by Riemann theorem, we know the existence of the canonical divisors for every function field, and for each canonical divisor, we can use the characterization in terms of their degree and the dimension. And by the assumption, in this case, it is going to have degree 2 and it has dimension 2. So this shows us the existence of such a divisor. Then from the first item, we can conclude that F is indeed hyperelliptic function field. Of course, the elliptic and the hyperelliptic function fields are the deeper topics, and you can find more details, particularly in chapter 6. However, for instance, if you compare the rational elliptic and hyperelliptic function fields, as you increase the genus to decide the structure is getting more complicated, and the things we can say are in some sense limited, and we need more information about the structure of the function fields. However, for the moment, as a two example, or what kind of differences do we have, or what kind of characterizations do we have, to see that it's enough to consider these 3 simple cases. So, okay, this is all I want to say, and see you next week. Bye-bye.